Good morning. It's nice to see you all. It's gratifying that so many people would come in out of such a nice day to hear my blathering. So I have been teaching a class for non-science major undergraduates at the University of Chicago about global warming for about, I think it's 13 or 14 years now, and it has it's sort of a distributional requirement kind of a class, so they can take it, an English major can take it to satisfy their science requirement. And so I don't really assume that they have any prior knowledge, about anything scientific. And part of the goal of the class is to sort of introduce them to the way that scientists think. And I think that, by sort of focusing in on this one question about global warming in particular, and where does the idea come from, and what does it mean, and what would it take to deal with it, I think they actually get a better idea of how real scientists, think, rather than, sort of a survey class of, this is the Miocene and there are dinosaurs and da-da-da-da-da like that. So I wrote this textbook a few years back, which goes with the class, which will have most of the stuff that I'll show you today. I've got another one, and it's been sitting up here shamelessly, plugged for the last 10 minutes. I apologize for that. I wasn't thinking. I've got another book which is intended for a sort of more voluntary audience. This textbook you make people read because it gives them a bad grade if they don't. But the other one, it will come out in around the end of the year, called The Long Thaw, which is, I actually wrote it with my parents' sort of church discussion group in mind, people who had sort of it's about the way that climate change will will persist for essentially forever, thousands, hundreds of thousands of years. And so, thinking about those kinds of time scales kind of takes you out of yourself a little bit. So anyway, one other resource that I would mention while I'm on the topic, when I did the class this last time, I always have the students read some other book just to give some other author a chance to sort of come up to bat and try to talk to the students. And then I ask them a question or two on the exam and kind of leave it at that. And the one I chose this year I would recommend to you, it's by a journalist named Mark Linus. And it's called 6 Degrees. And it's got 6 chapters in it, one for each degree centigrade. So the forecast for the climate change in the coming century is from sort of 2 to 5 or 6 degrees centigrade change in the global average temperature of the Earth. And so what this guy did is he read all the literature about projections of climate change, and then divided it up into chapters. So if the Earth warms 1 degree C, which actually it almost already has, and it probably will given how much CO2 we've already released, what are some of the projected possible impacts of that, or 2 degrees, 3 degrees? And it really kind of brings home, it's a depressing book. It's just, you can't read it in one sitting. It would probably kill you. You'd be sitting in a coma.
Is that L-Y-N-N or
N-A-S. N-L-Y-N-A-S. Linus, Mark Linus, or Linus. I'm not sure how to pronounce his name. He's written a couple of other global warming books, but he's not a scientist, he's a journalist. He gets a little bit hysterical in some of the later chapters, but the first 3 or 4 chapters, as the warming gets more intense, the projections also get kind of, less, they get sort of more speculative. We're talking about, warming the Earth into a climate state that it hasn't been in millions of years, and so, the later chapters of the book are kind of not as just the science behind it is not as reliable as the early chapters. But anyway, I would point you to that as a good source. So climate, the forecast for global warming has a very long history. It goes back, it really starts with Joseph Jean-Baptiste Fourier, the guy that came up with the Fourier transform in mathematics. He was a mathematician in Napoleon's army, and he published this paper in 1827 where he described the greenhouse effect. So the basic idea, we can start with the Earth, and it has this energy balance. Energy comes in from sunlight, and then it leaves as infrared light. And the way the temperature of the surface of the Earth is determined is by what temperature the Earth has to be to balance the energy budget, so that what goes out balances what comes in. So this is a formula for energy coming in from the sun. So this alpha term is the albedo, the reflectivity of the Earth. So clouds reflect sunlight back out to space. And then here's the Earth. And then the way that objects radiate infrared light is they follow the Stefan-Boltzmann law, which is here. The rate of energy flux in watts per square meter is epsilon, which is a property of the object, which is pretty close to just 1 for most things. Sigma is the Stefan-Boltzmann constant. It's just a number you can look up in a book. And then here's the temperature of the Earth in Kelvin raised to the 4th power. So the higher the temperature is, the more energy is leaving the planet. So I like to make an analogy, and actually this analogy comes up about 8 times throughout the class in totally different contexts. It's very an analogy of a sink. So you have a faucet, and you're running water into the sink, and then the water level builds up in the sink, and then it's running down the drain, and how fast it goes down the drain depends on how much water there is in the sink. So you start out, and there's more water coming in than going out when you first turn on the faucet, and it sort of builds up, and then it reaches the level at which things balance, and then it stays there. So that's sort of the equilibrium level. So it's, you know, how fast it goes out depends on the water level. So that is analogous here. This is going down the drain. The water level is the temperature of the Earth. And so you'd start out, say you started out with a planet that was very cold. That would be like turning on the faucet to an empty sink. The temperature would rise because there'd be more energy coming in than going out, until finally it reaches the temperature where everything sort of balances. So you can solve this equation and end up with a temperature of the Earth which is way too cold. So without the greenhouse effect, we couldn't explain why it's not, you know, freezing cold outside all the time. There's no dispute about the greenhouse effect. Okay, so what Fourier did is he said, we're going to put a pane of glass over this rock. And the properties of this glass are that the sunlight is going to get through without being absorbed. But then the infrared from the Earth is going to get absorbed by the pane of glass because it's selective in that way. And then the pane of glass itself is going to radiate infrared light, both going up and going down. And the rate of the infrared emission is always given by the temperature of the body, the Earth in this case, or the pane of glass can have a different temperature here. Run through that Stefan-Boltzmann equation, epsilon sigma t to the 4th. So now there's this, you can solve for the steady state temperature of the pane of glass and also the temperature of the Earth. So it's 2 equations and 2 unknowns. And some of my students just weep blood trying to this is a story problem. And so they just crumble into a pile into a puddle on the floor. But you can solve it, if you start from a boundary to space and you want to set incoming energy equal outgoing energy, then that can tell you the temperature of the atmosphere, and then you can kind of work your way down. So there's an algebraic way you can kind of get them. I mean, if this is where you're going, you can get them to solve this thing. But the point is that the temperature now of the ground is warmer than it was without this pane of glass, just by balancing the energy budget for the ground. So coming back to the sink analogy, it's like you've got the thing going, and then all of a sudden a little piece of carrot or something falls on a strainer over the drain, and it kind of impedes the energy going out. And so now the water level has to rise in the sink until you get enough pressure from the higher water level to push the water down the sink, and it reaches a new equilibrium with a higher water level. So, the piece of carrot there doesn't create the water. It just kind of traps the water as it's passing through the system. The same way that the greenhouse gas doesn't create the heat. It just traps the heat from the Earth or from the sun as it's passing through the Earth system. So moving along in time. So I'm just using this figure here, which I showed you before with Fourier off on the edge. That must have been very confusing to you. I'm just using this as a timeline. But what this figure shows actually is the average temperature of the Earth over the time when there have been thermometers, which, Gabriel Fahrenheit invented the thermometer back sort of around in here, and the centigrades, you know, they can calibrate thermometers fairly well because water has very definite melting and freezing points, and so you know, thermometer measurements from a long time ago are pretty reliable, as opposed to, say, CO2 concentration measurements or ozone chemistry or something like that. You kind of have to figure out what the hell they were trying to do. But temperature, there's good records going back a long time, and so you see this kind of uptick. And really, the smoking gun for global warming starts about 1970. We'll see in a couple minutes. You know, there's natural variations, but we can't explain this recent uptick in the temperature of the Earth without the fact that the CO2 concentration in the atmosphere is going up. Okay, so moving along this timeline now, is this British chemist named John Tyndall in 1859 who discovered that some gases are able to act like that pane of glass in Fourier's greenhouse by absorbing and emitting infrared light, and other gases aren't. So this is the structure of carbon dioxide. It's a linear molecule with the carbon in the middle and the two oxygens on the sides, and it's symmetric. And the thing that has to happen if a gas molecule is going to interact with the light is you have to vibrate the bonds in a way that creates some asymmetry in the electric field. So the simplest gases in the, well, so the main gases in the atmosphere are oxygen and nitrogen. So it's just two atoms, and they're the same, you know, two oxygens together. And you vibrate that, and it never breaks the symmetry. So, you know, the one oxygen atom is pulling on the electrons just as hard as the other one. And so nothing you do to that is going to create an electric field that the light, which is, you know, comprised of an electric and magnetic field, that the light can kind of get a grip on. So oxygen is not a greenhouse gas. CO2 is a symmetric molecule also, and so at first glance you might think that that's not going to do anything either. And if you do a symmetric stretch, so if my head is the carbon and my fists are the oxygen, a symmetric stretch like this, that won't interact with infrared light either. But there are vibrational modes of this molecule and any other that has 3 or more atoms in it, which do break the symmetry. So the bend, which is kind of like this, you know, right now the oxygens are partly negative and the carbon is sort of partly positive. Oxygen is very greedy for electrons. And so now you've got a sort of negative charge on one side and positive on the other. And then when it swings the other way, you've got negative on the other side and positive here. So you swing that back and forth on the frequency of its natural vibration, which is set by the springiness of the bonds and the weights of the atoms, and you can create light. Or light coming in with that frequency can excite this motion and be absorbed. So this bending motion is, can act as a greenhouse gas, like in Fourier's thing. Or you can do an asymmetric stretch, which is kind of like this. And that also makes a dipole moment and absorbs. That was one of my best tricks. I mean, everybody else, I can't believe you didn't. Water is also a greenhouse gas. Sometimes you hear people say, well, water is a more important greenhouse gas than CO2, so why worry about CO2? The way water vapor works, actually, is that the concentration in the air is set by the hydrological cycle. If you get too much water evaporating, it'll just rain out. And so if you run a sprinkler, you don't, you know, contribute to global warming because it'll just rain out. The water that evaporates from your sprinkler will just rain out someplace else fairly soon. But when the climate warms, the warmer air can hold more water vapor, and so water vapor acts actually as a positive feedback. If it weren't for water vapor, you know, putting more water vapor in the air when you warm the planet, we wouldn't really even have to worry about global warming from CO2. The water vapor sort of doubles or more the warming impact from the CO2. So just because water vapor is an important greenhouse gas that's not CO2 doesn't mean we have, you know, no reason to worry. Svante Arrhenius, he calculated around, you know, 100 years ago that doubling the CO2 concentration of the air would increase the temperature of the Earth by about 4 to 6 degrees C. And that's real close to the present day, you know, from the IPCC, the Intergovernmental Panel on Climate Change. They say now 2 to 5 or something like that. to a certain extent, Arrhenius was lucky. I mean, there were all kinds of things. Actually, this is my favorite paper in all of Earth Sciences. He didn't know how much infrared light, CO2, and water vapor would absorb, but he made use of measurements of the infrared intensity of moonlight. This guy named Langley was trying to figure out how warm the moon is, and so he made measurements of infrared light to use that Stefan Boltzmann relation, sigma t to the fourth, to figure out how hot the moon is. So sometimes the moon is, at a oblique angle, and it's coming through a lot of air. Sometimes it's coming straight down, and the humidity of the air changes. So Arrhenius used the data to back out what the absorption coefficient for the CO2 and water vapor is. And then he did this calculation, all with pencil and paper, on a grid, just like they do climate models today. It took him 2 years of what he called tedious calculations to come up with that number. It's just an astonishing thing. So he figured out this water vapor feedback. So I have these diagrams that I made up. So this is a state variable, the temperature of the Earth, and you increase it by some external cause, like put CO2 in the air, and that affects the water vapor concentration. You get this sort of loop of cause and effect, where the water vapor concentration increases the temperature still further. And if there are cases, like on Venus this happened, where this thing kind of runs away. It's called a runaway greenhouse effect. So then the oceans boil, and the water gets blown apart in the upper atmosphere, and the hydrogen escapes to space, and that's that. And we know that's never happened on the Earth, and it's not likely to happen in the next billion years or something like that till the sun gets hot. But it is a phenomenon. Another feedback that Arrhenius figured out is called the ice albedo feedback. So you warm the temperature of the Earth by some external thing, and you cause ice to melt, and ice is very reflective. So snow and ice reflect sunlight back out to space. So if you get rid of the ice, especially sea ice, actually, the sea ice is very reflective, and then the ocean, if you melt the ice, absorbs some of the least reflective stuff on Earth. So the ice in the Arctic is melting back. This is the closest thing I know of to a tipping point in the climate system, is the sea ice in the Arctic. And that's going to have a huge, huge impact, causing sort of further warming. Yeah?
I just want to ask what you talked earlier about the effect on CO2. Is it that bending of it that gives it that property then? To be a greenhouse gas?
Yeah, so both the bending and the asymmetrical stretch can absorb infrared, but the important thing here is whether the vibrational frequency of the molecule is the same as where most of the infrared light from the Earth is coming from, which depends on the temperature of the Earth. And it turns out that you're right, the bending is the one that has the most traction at absorbing the infrared light that's there, that's trying to make it out to space. Yeah. So this ice albedo feedback is most important in the high latitudes. And so in this climate simulation of temperatures by the year 2300, if we burn all the coal, so this is a real Dantean kind of a simulation. But you see much more warming in the high latitudes than in the low latitudes, and this is mostly because of this ice albedo feedback. And in fact, you see much more intense warming today in the high latitudes in Alaska and the Arctic than you do in the low latitudes. There's another good book I can recommend to you. It's by Elizabeth Colbert. It's called Field Notes from a Catastrophe. And she starts it out, so she goes around and interviews scientists and drives around with them in their pickup trucks and sees what they do and talks about what this all looks like on the ground. It's a very personable book. She originally published these as a series of articles in the New Yorker. And so her first chapter was some guy up in the Arctic who was researching permafrost. So it's more intense up there because of this ice albedo feedback. And Arrhenius figured this out over 100 years ago. David Keeling started measuring the CO2 concentration in the air, and he was like a lab nerd. He didn't, he just wanted to make this measurement better than anybody had ever made it before. He just got this kind of bug under his saddle to do this, and he started out in sort of, just going outside and taking some air samples, but he found that there was all kinds of local kind of noise that got all kinds of variability. He wasn't getting a reproducible thing. And so he eventually started making measurements from Mauna Loa Mountain on the big island of Hawaii. So, this is this very tall mountain sticking up into the, into the remote marine troposphere, as far away from, local effects as possible. And, there were power outages and calibration issues, and it took a few years before, so they could see the seasonal cycle in the CO2 concentration of the air. And then it took a few years before they could also see that it was sort of trending upward. And that was because of human activity. So this is a movie of where the seasonal cycle comes from. This is a satellite product called NDVI, which is a vegetation index. So this just shows it's sort of the greenness of the Earth. So you can see the red is kind of winter, and then the blue is the greenness. And so you see the leaves coming out and kind of moving up into the north in the summer and then going away in the winter. So if you kind of really blur your eyes and look at this, it kind of looks like, you can kind of see that the world is sort of dominated, the land surface of the world is sort of dominated by the northern hemisphere. It just turns out that there's more land up in the northern hemisphere. So the farther north you look in the atmosphere, the more of this seasonal cycle of the plants breathing you see. So there's another one. This is now a plot of the CO2 concentration in the air as a function of the latitude of the Earth. So there's 90 south at the South Pole. They take some measurements. And here's the equator, and here's 90 north. And we're starting in the year 1979. So this is after, the Mauna Loa record started first in the mid-50s, and then they started doing more and more of these stations. And so we're going to watch this thing progress forward through the seasons of the year, through time until 2004. So you're going to watch the Earth sort of breathing. Isn't that wonderful? So most of the land is in the northern hemisphere, so you can see the seasonal cycle is more intense in the northern hemisphere. You see these occasional, flying points that are probably local, sources or sinks of CO2. And then, of course, you see the general rise of the CO2 concentration in the air. So the rate of CO2 going up in the atmosphere is only about half as fast as the CO2 that we release from fossil fuel combustion and deforestation. So you could occasionally hear people claiming that CO2 is going up for natural causes maybe 15 years ago, but they've long since given up on that. That's just an untenable argument. The ocean and the land surface are sucking up half of the CO2 we release, so we're releasing more than enough, twice as much as would be required to explain this. Also, the ice core data, there's bubbles of ancient air stored in ice cores, and so we can see what CO2 levels did in the past. And it was very stable for very slow rise over 10,000 years since the last ice age, and now it's shooting up through the roof. So absolutely no question that this is our doing. So in 1990, the first of these reports from the Intergovernmental Panel on Climate Change, which is this United Nations organization where scientists who don't work for the UN, who work for universities and government labs and things like that, but are recruited to write these reports that sort of summarize the state of climate science. And these reports have come out every 5 years or so, and the most recent one was just last year in 2007. And you can download the PDFs of these. You don't have to buy the book. In particular, there are a summary for policymakers and technical summaries that you can. If you want to fact check, if you want to find out, about methane in the atmosphere, sources and sinks, or hurricane intensity or something like that, this is the place to go because it really is a sort of encyclopedic treatment of all of this. Anyway, so the first of these reports was published in 1990, and they said you couldn't see global warming yet because of natural variability, but they predicted that you'd see it by the year 2000. Did you have a question?
Yeah, I was going to ask you to define noise.
I'm sorry?
I was going to ask you to define noise.
Oh, yeah. Well, just sort of natural climate variability. So they, in 1995, they found a discernible human influence on global climate. So it actually came earlier than they had initially predicted. And the reason why they say it's caused by people is because there are various factors that can drive the climate to get warmer or colder that are both natural or anthropogenic. So, and so there are basically 4 of them. And they're all plotted here on scale of watts per square meter of energy. So a watt is a flux of energy, like, you know, if you were talking about flux of water, it would be gallons per minute. A watt is just like that. For you know, joules per second is what watts are actually. So the intensity of the sun varies a little bit, both kind of drifting up and down on timescales of hundreds of years. And also, the reason why this is a thick line is because there's some variability in the intensity of the sun, which goes with the sunspot cycle, which is about an 11-year cycle. So there have been good measurements of the intensity of the sun since the 70s. Before that, there was, you know, records of how many sunspots there were going back to when Galileo first invented the telescope in the 1600s. And before that, they can piece together the intensity of the sun using these radioactive elements of carbon-14 and beryllium-10. So the idea is that when the sun is very intense, brighter, it has a stronger magnetic field, which deflects cosmic rays that are coming into the Earth from out in open space. Cosmic rays, when they hit the atmosphere, they create these beryllium-10 and carbon-14 atoms. So if the sun is intense, you won't get as many of those atoms, and you go to an ice core and you measure how many atoms of those things there are, and you find fewer of them accumulating in times when the sun was brighter. It's a really thin-sounding story, I know, but what you do is you calibrate it against things, you know, when you know what the sunspots were, and so you sort of figure out if it works or not. And then once you demonstrate that it's working over the time when you can test it, then you can sort of push it back. So a little bit brighter during sort of medieval time. There was a climate interval in Europe called the medieval warm time, which was, you know, a good time to be in Europe. Good harvests and a benign sort of climate. People sometimes argue that therefore warming is good for us, but medieval warm time was, you know, maybe a ½ degree C warmer than average in Europe, and the forecast for the coming century is like 3 degrees, 2 to 5 or something. It's totally apples and oranges to say that, you know, the medieval warm time means that warming is good for you. You know, it's like saying being pat on the head is pleasant, so I'll hit you with a hammer kind of thing. And then around here, there was the little ice age when the sun was sort of cooler. And there was actually times when there were, for decades at a time, when there were no sunspots whatsoever. So just a few decades after Galileo invented the telescope, there was this time called the Maunder minimum when the sunspots just disappeared. And then they came back sort of later. So that was a cool time. Volcanoes cool the Earth by putting aerosols, little droplets of sulfuric acid in the stratosphere. So it has to be a big volcano because you have to get the stuff all the way up into the stratosphere where it doesn't rain from, and so the particles can stay there for a while. So, you know, just your little Hawaiian volcano that's kind of going all the time doesn't really affect the climate. The last big one was Mount Pinatubo in 1992, and that cooled the planet down by about a ½ degree centigrade for like 2 years or something like that. So the radiative forcing in watts per square meter is very large from volcanoes, but they're very, very short in duration, you know, when you plot it on 1,000 years like that. Greenhouse gases are going up So CO2 is the main one. It accounts for a little more than half of the warming from greenhouse gases. The other ones are methane and freons, these chemicals that we use in refrigerators and air conditioners. And then laughing gas, N2O, actually, which has a source from soils. When they fertilize soils with nitrogen fertilizers, bacteria create a little bit of this N2O as kind of a byproduct, and it has a lifetime in the atmosphere of 150 years or something like that, and it's kind of just going up. Yeah?
You said you taught this in a non-science class.
Yeah.
In teaching the humanities, we're always talking about perception and who's biased and whose background are you talking about. Can it be unequivocally stated that greenhouse gases are caused by human influences? Or
Yes.
is that at all debatable as far?
No, that's not debatable. So the main one is CO2, and we're releasing more than enough CO2 to explain the CO2 rise. Plus, before we started doing that, the CO2 was constant, is stable. So that one's open and shut. Methane is dicier because there are human sources of methane, like rice farming and livestock. But there are also natural sources of methane, and it's very hard to really pin down the methane budget. So methane is twice as high today as it was several hundred years ago, which we assume is the natural system. But it has stopped going up, and we don't really understand why that is. It was rising strongly until about 1993, and then it just sort of plateaued and stayed stable. And so one story is that the collapse of Eastern Europe with leaky gas pipes or something, they make their economy more efficient, and that, I don't know if that's true or not, but it sort of gives you an idea of the desperation that people have to try to figure out what's going on with that. Freons, there's no other source besides people. And nitrous oxide, again, it was stable before a few hundred years ago. And although it's not totally clear exactly where it's coming from, actually a large fraction of it, maybe half, some astonishingly large fraction, comes from the country of Brazil, I read. I don't know how they know that, but it seems to be a tropical thing in particular. But the fact that it was stable before, I think, says pretty clearly that it's not natural now. Did you?
You mentioned the N2O. I was just curious. Hasn't the amount of nitrogen in the atmosphere stayed relatively constant? I mean, is there any connection between all of this?
Well, there's so much more nitrogen in the air that the amount of nitrogen that went into making N2O is absolutely trivial. You could probably. They measure, yeah. No, it's not going to run out of N2 anytime soon. Yeah.
Can you explain again the difference in width for solar contribution?
Well, there's just a little 11-year cycle in there going up and down, which you can't see because the time scale is so crunched together, and so it's just drawn there as a thick gray line.
My second question was, can you explain why there was a dip in greenhouse gases around 1600?
Yes, actually. So this is the Little Ice Age, and this is before anthropogenic, human CO2 sources are thought to have kicked in. And when the Earth cooled because of a sunspot cycle going away, the cooler sun, a cooler ocean actually absorbed some more CO2. So it's actually a positive feedback that and the same thing you can see in the glacial cycles, that when the Earth warms up, the CO2 goes up. When the Earth cools down, the CO2 goes down. So it's another positive, it's a loop of cause and effect that exacerbates climate changes. And so right now what's happening is the CO2 is going up and the oceans are absorbing the CO2, so it's acting like a stabilizing thing. But the question is, how long is that going to last? Yeah.
Yeah. On the chart, it looks like there's been a recent increase in the sun's intensity that sort of parallels the increase in greenhouse gases. So I'm wondering, unless that's just a noise that doesn't mean anything, is there any reason to think that the increase in solar intensity isn't related to global warming as well?
Well, so you're seeing an increase from like 1900 to 2000.
Right.
But the warming, I'll show you in a graph in just a second, that shows models trying to simulate the temperature changes of the Earth. The part that you can't explain without the greenhouse gases begins in about 1970 or 75 or something like that. And so from, I mean, it'd be hard to pull out of this plot, but since about 1970, there hasn't been a change in the intensity of the sun. So for that, you know, if you call that the smoking gun, there's no way you can fill that in with solar forcing. Yeah.
I went to a lecture by the famous skeptic from MIT.
Lindzen.
Yeah. You said it.
Dick Lindzen, Richard
Yeah.
Lindzen.
And,
He used to be in my department. That was before my time.
And he said a couple of times that there had been no warming in the last 10 years. He said it was going up like you're showing, but in the last 10 years it was just steady. Is that right?
The year 1998 was a particularly warm year because of El Nino. So, you know, there's been a sort of warming trend, but on top of that, there's sort of ups and downs. So, you know, you have a warming trend, but you have ups and downs. And so there's 1998, and so, you know, maybe it's exceeded that, you know, since then.
So
But to say that global warming ended in 1998 is the kind of thing that guy is famous for saying. You know, at some point, it seems to me you got to be honest with, if you're talking to non-scientists, and if you're presenting stuff that's sort of deceptive like this, I call that over the line. I refuse to debate people like that. There's a lot of skullduggery going on, I think, and Lindzen is well, I'll say no more. Yeah.
You mentioned freons, and I just
Yeah.
want to make sure I understand. There's no natural source for
Right.
freon.
Right.
That's a completely man-made.
That's right. Yeah.
Can you explain why water vapor? So water vapor is a stronger greenhouse gas, I've read.
Yes.
But you had said earlier that there's the natural fluctuation of water vapor with the hydrologic cycle. So when it gets warmer, the atmosphere can hold more water vapor.
That's right.
So why isn't water vapor the biggest concern in terms of greenhouse gases?
Because it's nothing we can control. We can't, I mean, if the temperature of the Earth warms, there will be more water vapor in the air. And there's nothing we can do about that except to control the warming by the driver, which is the CO2. If that makes any sense.
Somewhat. I guess I know we can't control water vapor, but it seems to be that would be the largest concern with climate change, is the fact that water vapor is stronger and it's increasing in the atmosphere as it gets warmer. So do we really have, if the climate's already changing, as it seems to be,
Yeah.
and water vapor is a stronger greenhouse gas, is there really much control we have anyway?
Over water vapor. No, cloud seeding or something like that. No, there's
Right.
nothing. No, it's you know, the water rains out when the air rises and it cools down, and then you exceed the saturation vapor pressure, and it rains. So actually, one of Lindzen's theories for a while was that when you put more CO2 in the air, it will cause the circulation of the air to go differently in such a way that it kind of wrings out water vapor out of the air better. So the relative humidity of the atmosphere would dry out, and so that would compensate for the CO2. And that theory, you know, I mean, that was a legitimate scientific proposal, and then when that was sort of proven to not work, he backed off on that. So that was entirely cool. But you know, it's just more recently that he sort of resorted to more deceptive sort of things. But how much in the climate models, and also apparently in the real climate, when you warm the planet, the relative humidity stays the same. The average relative humidity of the Earth is about 80%. So you make the planet warmer, 80% of saturation is a bigger number because saturation is a bigger number, but the relative humidity stays sort of the same. But if in the real world the relative humidity were to change with CO2, you know, which could be either direction, it could get more humid or less humid, then the amplifying effect of the water vapor, you know, could be stronger or weaker than is predicted to be. Arrhenius he also assumed that the relative humidity was going to stay constant. He didn't have any reason to say that. He just had to make it up because he didn't know it. But again, he was a lucky guy. Yeah?
I'm sorry, one other theory that a student was giving me the Earth's rotation on its axis as being the cause of global warming.
I'm not doing that.
All right.
Yeah.
Hadn't heard that one.
No.
Okay.
No, that's a new one. That is a new one.
I had nothing to say because I wasn't sure where it was going.
Yeah. So the fourth of these climate forcings is aerosols, which are from coal power plants mostly. These are in the troposphere. So, and they tend to cool the planet. When these aerosols, sulfuric acid is what they are, and they rain out, they cause acid rain. And so when societies get rich enough to afford to deal with this, they tend to, like the US has, managed to scrub a lot of the sulfate out of our coal flue gases to reduce acid rain. So in that case, this thing gets reduced back down. So it's a question how much of the warming from the greenhouse gases has been masked by these aerosols. And the aerosols in the troposphere, since that's where the rain is coming from, they only last a week or two. We burn high sulfur coal here in Ohio, and it rains on the nice people in New York. It's just not that distant, not that far away. And so, if we clean up the coal system, we can remove this cooling effect and then leave just the warming effect from the greenhouse gases, which persists for a lot longer. So this is now one of the central plots from the IPCC report. There are different versions of this, but it shows the observed temperature of the Earth over the instrumental temperature, over the last century or so, which is this black line. And then it shows in this sort of red color the model results of what the temperature of the Earth should be. The red color, they include all four of those climate forcings. And in the blue, they don't tell the models about the human-caused climate forcing. So they don't tell them about the rising CO2 concentration and the aerosols. And so this is a plot for the whole world. These are plots for various regions. So you can see there's more warming in the ones that are higher latitudes and less warming in the low latitudes. More warming over land than on the ocean. But the basic point is that unless you tell the models about the greenhouse gases, they can't explain that recent warming since sort of 1970. So that's the smoking gun, is sort of the temperatures since the 70s. So people like Mr. Lindzen, Professor Lindzen, will say that the sun. Maybe the sun is doing something that we don't understand. When you have variation of the intensity of the sun, most of that variation, or a lot of it, is in the ultraviolet. And a watt per square meter of ultraviolet light is not just energy on the ground. It creates ozone in the upper atmosphere, which is a greenhouse gas. And there's all kinds of possibilities of ways that could be more important to climate than we understand. Clouds are very difficult to model. You can't model them from first principles because they're governed by all kinds of little effects, little winds and microphysics of cloud particles coagulating and things like that. And so the clouds in climate models are they're what they call parameterized. So, if the relative humidity is this and the temperature is that, then let's put in this kind of a cloud, and it'll have this kind of a distribution of cloud droplets. And the size of the cloud droplets is crucially important to determining the reflectivity of the cloud. So, it's something that you want to just really nail right, and it's something that we, are never going to have the computer power to do what we really would like to do, which would be to resolve all that physics, starting from Newton's laws of motion and thermodynamics, and then have the clouds kind of emerge, the way they do in reality. That's just not going to happen. So people like Professor Lindzen will say, they're blaming CO2 because they just can't think of anything else. So I like to sort of frame this as a detective story because, people always put on their thinking caps with detective stories. So you walk into the room and there is the butler, and he's got a smoking gun in his hand, and there's the dead guy with the bullet hole. So this is a high-profile case, and so your boss is riding your butt on this. And you got to write all these reports. You got to check everything out. So you find out that that he bought the gun, and the bullet came from his gun, and it was just recently fired, and it's got his fingerprints on it, and da 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 da. Everything works. There's no sort of no fly in the ointment here. Everything sort of makes sense. But your partner is sort of a contrary guy, and he says that he thinks the chauffeur did it. And so you check it out, and you find out that the chauffeur was in Kentucky for his sister's wedding, and 50 people saw him there. And you don't see how he could have done it, but your partner says, well, you're just not smart enough to figure out how the chauffeur did it. And it is very difficult to prove a negative that the chauffeur did not do it. But on the other hand, if your partner wants to convict the chauffeur, he's got to make the jury understand why the butler was standing there with the gun in his hand. Some innocent explanation for that butler. He's got to unconvict the butler. So the situation here with climate change is that we can explain the warming perfectly well with the CO2 and other greenhouse gases. And if you want to say that really the world is such that you can dump as much CO2 in the air as you want and it won't change the climate, then you've got to explain, for one thing, why the Earth has been warming over the last 20 years. So maybe it's the sun, and the ultraviolet and the ozone and all that sort of stuff. But then you also have to explain why the CO2 is not going to warm the planet the way everybody has always calculated that it should, all the way back to Svante Arrhenius 100 years ago. So, it's an open and shut case against the CO2. You got to get the CO2 off the hook. It's like you got to come up with two impossible things in order to make this work. So how are we doing on time? We're a little more?
15 minutes.
Yeah, okay.
Yeah.
So some of the impacts of climate change, everybody wants to know, what is there to worry about? What's the big thing? To me, it seems like the thing that I worry about the most is drought. So there's a great discussion in Linus's book, actually, about this. During the medieval warm time, 1,000 years ago, it was great in Europe, but the U.S., the Southwest, in fact, globally, the world was sort of a droughier kind of a place. In the American Southwest, like in Nebraska, not Southwest, but it's sort of the plains. Nebraska, according to Linus, there are fossil sort of dunes. So you've ever seen, some Omar Sharif movie in the Sahara, where there's these sand dunes. That's what Nebraska looked like at some point in the distant past. There's a lake in California called Mono Lake, which from medieval time, there are fossil tree trunks. So these trees grew fairly large. So that means that there was a large span of time when there was absolutely no water in this lake. Sort of associated with that time. So these are some plots from the Hadley Center climate model, which is one of the leading climate models. I mean, there are about 20 of these models that submitted results to the IPCC that we saw in the two different, the red and the blue things. There was 20 different models. But the Hadley Center model has always been kind of one of the leaders of the pack. And they're showing in the black line the percentage of the land surface which is in drought conditions. So the black line is from the real world. And drought is a hard thing to define because it's not just inches of rainfall. It's inches of rainfall compared to what the landscape is used to. So, someplace that's always dry, if it's dry again this year, you don't consider that a drought. So they have this thing called the Palmer Drought Severity Index, which is, compares the conditions, not only the rainfall, but also the soil moisture, which takes a few years to change, compares that to kind of the norm. And there has been this sort of uptick in the observation since about 1980 or 85 or something, a little bit in the percentage of the Earth that's in drought conditions. And then these gray curves are what they get from their climate model So the top panel is where they just have an atmosphere, and they take the sea surface temperature from data, and they kind of drive the atmosphere model from that. And they claim they can sort of see that uptick, and I guess I can see. I'll give them that. And then here, this is the same thing, but they have, this is a coupled model, so they're letting the ocean, evolve according to what it wants to do too, instead of driving it. And here it's not really so obvious that they capture that, but there it is. It's not bad. So then the real kicker comes in the next figure in their paper. They're starting out from the year 2000. They're defining these 3 different categories of drowtiness. So extreme drought is something like is the most the driest 5% of the Earth's surface. So let's take a snapshot today. You calculate this Palmer Drought Severity Index, and then the worst cases, 5% of the ocean of the land surface. They call that extreme drought, and then they take that same index and they trace it through into the future and see how it changes with climate change. And you see that it's going up, and then by the end of the century, we're talking 30% of the land surface. So, this is dodgy. The impacts of climate change that will probably have the most effect on people are these sorts of regional things. Australia has been really dry for the last 8 years or something like that, and it's totally changed the Australian government's view on climate change. They were holdouts against Kyoto like we were, and now they've passed legislation making incandescent light bulbs illegal. And different models tend to disagree. Some of them might have predicted that Australian drought, and others maybe would not. So the global average temperature of the models are, they're there. They are in accord with each other. But in terms of the regional impacts, which are probably the most severe, like droughts, they are. It's harder. It's a harder forecast to make, and that means that it's sort of harder to prepare for. But if you start, when you lock land in drought, it changes the vegetation, so you get sort of locked in to that drought sort of a condition. So the changes tend to be kind of abrupt, like a flip-flop from kind of a lush countryside to a dry countryside. And there's really, after a few years, you can't store water, you can't truck it around. There are other exacerbating things about water, like mountain glaciers and snowpack tend to save winter precipitation and then dribble it out slowly over the summer, which is when you want it. So Lima, Peru is sort of the poster child for this, but the Pacific Northwest and California also get a lot of their summertime water from mountain snow. The Himalayas, so Al Gore in his excellent movie made the observation that 50% of the world's population is drinking water that comes at least half from transiently melting mountain snow and ice, which I think must be the Himalayas, feeding water to India and China. But so if that all goes, that's a big deal. Yes.
2 questions. One, how come each type of line, there are 3 of each type of line instead of
Good question.
solid one?
Can I answer that first, and then you can answer a second? So there's variability in these climate models, weather, random stuff, chaos, the butterfly effect. So what they do is they run an ensemble of models. They run each scenario multiple times with slightly different initial conditions. And so, you put a butterfly into one model and a different butterfly into another, and they diverge, and so you can kind of get, it gives you an estimate of, the range of possibilities. You get a more kind of reliable, signal if you run the thing multiple times. So you're not interpreting every little wiggle. If you just run it once and interpret every little wiggle as being meaningful, you're probably going to get a lot of garbage.
Okay. My second question. It seems that, looking at the graph, the increase in one type of drought will cause an increase in another type of drought?
Well, so they define these different things. So moderate, severe is the present 10% worst, and then moderate is the present 25% worst, and so then they just track all those three, and they're all increasing. Yeah.
So that does mean an increase in one will cause an increase in another type of drought. Is there a correlation there?
Well, so the worst 10% will be included in the worst 25%, I suppose. But it's just showing that at all different levels of severity. Now the overall rate of rainfall globally will increase in a warmer world because the warm air holds more water vapor. The overall rate of precipitation is expected to get wetter with warming. So I guess the effect that we're looking at here is that, in general, the models find that places that are dry today get even drier with climate change. Places that are wet today get even wetter with climate change. So it's not like the whole world is going to dissipate, but they're just finding that the dry places here are getting drier. Yes?
Could you clarify the report, which I really probably am not going to be able to even explain, but a recent report that appeared in either Science or Nature, which I believe said that re-examination of data or remodeling or something like that has shown a different amount of absorption in the oceans, which will cause the next 10 years not to experience heating, but after the next 10 years to have even more heating than what previously been expected.
Yeah. So I work on this climate science blog site called realclimate.org. And with some of my collaborators on that site, we proposed a gentlemanly wager with the authors of that report that that we didn't buy it, and we proposed 5,000 euros. So it was my German colleague, friend of mine, who came up with this idea. He sort of spearheaded this. He said that he wanted to do euros because in 10 years, who knows what the dollar will be worth. But they never took the wager. This was. Without going into the details, so one of the time periods that they forecast the temperature change is already sort of half over, from 2005 to 2015 or something like that, and they predicted that would be colder than the past 10-year period, and we already know that it's warmer so far. So for them to be right on that one would require things to chill down a whole lot in the next couple of years. And then they also, with their method, predicted what it would have been the time period, the 10 years before that, and they got that too cold. So they missed 2 out of the last 2 points. And so the next one, is there any confidence in that? I think that nature tends to go for stuff that gets headlines a lot of times. Science too, to some extent, but nature is sort of worse in that regard. I don't think that paper is anything to take to the bank, frankly. Yeah.
Completely different. Linson, as far as I can see, is one of the very, very few really competent scientists who take a skeptical view.
Yeah.
And when you talk about this kind of thing with people who are skeptical themselves but not scientists, they bring that up. They say, well, there's this very smart guy at MIT who says such and such and such and such. It would help in arguing with him if I had some kind of a backstory on him. In other words, Mike could say he's crazy.
He doesn't believe that cigarettes cause lung cancer.
He doesn't?
No.
That's enough, right there.
So the last thing I wanted to show, and then, cut me off whenever, okay, is that this is something that I'm kind of, wrapped up about. And so this book that's coming out in the fall is called The Long Thaw, is all about this point. People have the impression that global warming is kind of a 100-year sort of an issue, because all the forecasts go to the year 2100, and you can actually see in a lot of places an atmospheric lifetime of fossil fuel CO2 as 100 years or something like that, which is a misconception. So this is a plot of the CO2 concentration in the air plotted as the airborne fraction of a total slug, how much carbon we release over the total fossil fuel era. So it goes up as the CO2 is being released, and then at some point you run out of coal or something, and the CO2 starts dropping because it's going into the ocean. And so this dropping to go into the ocean takes, centuries. So that's where the idea of centuries comes from. But it doesn't all go into the ocean. Even after it equilibrates between the air and the water, and all of it has gone into the ocean that wants to, there's still this leftover fraction, maybe 25% or something, that stays in the air. So if the ocean was infinitely big, then it could take all of it, but it isn't. It is what it is. And so it takes most of it, but not all. And then it leaves this sort of long tail of atmospheric CO2 that reacts with rocks in the rock cycles, dissolving calcium carbonate. CO2 is an acid, calcium carbonate is a base, and so they neutralize each other, and that takes up CO2. And then igneous rocks take up the last 10% or something like that on a time scale of 500,000 years, something like that. Very, very, very long response, lifetime. So this is data from the geologic record 55 million years ago. It's an event called the Paleocene-Eocene thermal maximum. And so things were going along just fine, and then something that was a lot like our fossil fuel era happened, and all this CO2 came out. It's not clear where it came out from or how much of it there was. The temperature of the ocean warmed up, and then it took 100,000 years for the CO2 and the temperature to recover. So, it wasn't a 100-year event then any more than it will be for us. The first 100 years will be the most intense. That'll be that spike. But the overall duration is much, much longer. And the one reason to care about that is sea level. This is a plot of the sea level of the Earth plotted against the average temperature of the Earth through geologic time. So the last glacial maximum is here when it was 5 or 6 degrees colder and sea level was 120 meters lower. Here's today, and here's times in the more distant past when it was warmer and the sea level was higher. So for contrast, this is the forecast for sea level rise by the year 2100 from the IPCC. 3 degrees of temperature warming, more or less, and only 0.5 meter of sea level. And the reason why it's not on this line is because it takes a long time to melt ice sheets, is what sort of the implicit assumption. But if ice sheets melt faster than they think they can, which there's many indications, which I'm not going to show you because I'm out of time. The Greenland ice sheet is already kind of rumbling and accelerating and surging and things. So it seems like it could be faster than what they forecast. At any rate, the CO2 will be in the air for thousands, tens of thousands, hundreds of thousands of years, plenty of time for ice sheets to melt, even if they're as sluggish as the ice sheet models are. And so we're not talking 0.5 meter of sea level rise. Ultimately, we're talking about tens of meters of sea level change in the fullness of time. And that's a huge deal. So one of the hot spots on the Earth is actually the east and Gulf coasts of the U.S. And Florida gets clobbered from both sides. Lots of low-lying area here. In China, the Yangtze River Delta. The river deltas are very low-lying. They're very fertile. They have a lot of population. A lot of people live in them. Bangladesh, you've heard of. I think that on the long term, we're like sacrificing the carrying capacity of the planet for a few decades of convenient energy. It's just lunacy. So I'll stop so I don't have to get cut. Thank you.
Do you have a question?
Yeah, just the yellow at the top, is that borders, or is that the same yellow that's at the bottom?
The yellow at the top.
Around the Great Lakes?
I think the Great Lakes are forecast to dry out a bit. Actually, the falling lake levels that we see already. It's not clear. I've seen one study written about in the newspaper. I just read about it. I'm not up on this, but saying that broadening the channel where the water flows out through the St. Lawrence or something has allowed the water to sort of flow out more quickly. And others say that it's changes in precipitation that are causing the lake level to dry out.
I thought there was the wobble of the Earth on its axis can affect incoming solar radiation, and there's sort of a natural cycle with that. So maybe that's what that student was referring to.
Could be.
Yeah.
And then I have a second. Okay.
Do you want me to talk about that?
Is that true, or
trying
to help her maybe?
There are these natural cycles in the Earth's orbit, and what seems to be important in terms of the glacial interglacial cycles, which have dominated Earth's climate for the last 2 million years, is how intense the sun is in the northern hemisphere summer. So, the northern hemisphere is where the land is to make ice sheets, and the summer is when you decide whether to melt back last winter's snow or whether to keep it and start making an ice sheet. And so those change on timescales of tens of thousands of years. So they can't explain something that happened since 1970. But actually, where we are with that is that if anything, the intensity of the sunlight in the northern hemisphere summer is getting low enough that we're close to the threshold at which, in a natural world, the Earth might go into a glacial stage. So that factor is actually tending, if anything, to cool the planet. On the other hand, the Earth's orbit is also very nearly circular now. It sort of goes through this cycle over 100,000 years between being kind of elliptical and being circular. And if it's circular, it doesn't matter which direction the northern hemisphere summer is, on the path of the orbit, because it's all the same. And the last time the Earth's orbit was circular like this was about 400,000 years ago, and that was a time when an interglacial interval like ours lasted for 50,000 years or something. So when they first started figuring out the ice ages, the timing of them, the last couple of them have lasted about 10,000 years, and our own has lasted about 10,000 years. So there was some discussion about, is the party coming to a close sometime in the next couple of thousands years? And you sometimes hear people say that climate scientists in the 70s were forecasting the next ice age, and now they're forecasting global warming, so they're obviously nutcases and should be disregarded. And that's a total exaggeration. Nobody said that, the Earth was going to cool down. There was a National Geographic article that kind of got a little hyperventilating, but that is sort of a made-up story. Did you have a second question?
Yeah. In terms of, it's feast or famine with precipitation in terms of climate change.
Right.
And you said, greater temperature, more water vapor equals more rain.
Right.
But what's the easy way to explain to people why there would be greater drought?
So when sunlight hits a surface, that energy can be carried away either as infrared or as water vapor, so latent heat. And so one application of this is the urban heat island effect. A city doesn't have the vegetation to supply this water, and so it has to lose its heat by warming up. And so cities are always hotter than countrysides. A green roof, the point of that is to have water up there to evaporate to carry away that heat. So now, if we increase the temperature of everything, we start drying out the land surface of the water vapor, and so it just gets drier. That's as close as I can. I can touch bases with a couple of these things that people may have heard of, but why exactly, it should go into drought in places. There's this overturning circulation of the Earth. The air tends to rise at the equator, so you get these massive convective clouds, and then it tends to fall at sort of 30 north and 30 south, and so those are the sort of desert belts of the world. And so it's places like that that tend to dry out. But I can't give you a better, kind of seat of the pants explanation, because it's a dodgy calculation. I mean, different models, they give different things. It's kind of right on the edge of what can be forecast. But there are there's sort of a correlation in the past. Also, the medieval warm time, for example, was sort of droughty around the world, and the last 20 years have been sort of more drought prone. So, you know, it seems like a reasonable way to bet. The classic Mayan civilization was apparently sort of wiped out by getting clobbered by a couple of decade-long droughts.
Great. Well, thank you so much.